So that uniform circular motion example is kind of neat, right? You get v squared over r, you get it a lot more easily than you would in Cartesian coordinates. But let's actually do something that gives you a little bit more insight than that does. Because in some ways, that's like, it's a result you already know, right? So what's so interesting about that? Let's instead talk about, say, a case where someone's going around in a circle, but going around faster and faster and faster. They're accelerating around the circle. So if we think about that, that's a case of non-uniform circular motion. Right? So the sort of idea is that I start out and I go in a circle slowly and faster and faster and faster, and so on and so forth. How would I describe that? Well, certainly one possibility is to say that actually the angle is not just increasing linearly in time, but maybe it's increasing quadratically in time, just to make something up, whereas the radius is staying the same, right? So we'll again have the radius be big R, but on the other hand, we're going to say theta, instead of being omega times t, maybe we'll make it alpha times t squared. I guess I should make it 1/2 alpha just for the sake of having the derivatives come out nicely. So alpha is what we would call the angular acceleration. It has units of radians per second squared, right? And so if you think about this, this says that as time goes on, theta increases faster and faster and faster, okay? So once again, my position vector is r times r hat. It's big R times r hat because, of course, r is not changing. My velocity, right, is dr hat by dt. Well, what's dr hat by dt in this case? Again, it's going to be r times theta dot times theta hat. But now theta dot, right, well, that's d theta by dt, is simply going to be alpha times t, right? So it's r times alpha times t in the theta hat direction. And notice that we still have the case that the velocity is always directed along the circle, right? Which makes sense. You're still moving in the circle, but the size of that velocity vector starts out small, gets bigger, gets bigger, gets bigger as time goes on. What's the acceleration, though? And this is where things start to get a little bit more interesting. So the acceleration is the time derivative of the velocity, right? Which is the time derivative of r times alpha times t times theta hat. Okay, now we've got two things that depend on time. Obviously, t depends on time, and theta hat depends on time as well. So let's take the derivative there. We're going to get r times alpha times theta hat, right? When we do the product rule, we'll first take a derivative of t, we'll get a constant one out of that. And then we're also going to get minus r times alpha times t times theta dot times r hat. In other words, I get r times alpha theta hat minus r times alpha squared times t squared times r hat. Which is kind of weird, right? What is that? What's going on with that? That says that the acceleration has both a component that is radial, and it also has a component that's in the theta hat direction. What is that? What do each of those mean? Well, this component that's radial is fairly easy to understand. In fact, if you look at it, this is simply r times alpha times t squared. Well, alpha times t is whatever your current angular velocity is. So this is r times omega squared times r hat, right? This term is what you call the centripetal term, right? It's centrally directed, it's going towards the origin, and the size of that acceleration depends on what the current angular velocity is. In other words, what that is saying is that as the velocity changes direction, there's this sort of steering term, right? The turning acceleration is r times omega squared times r hat. My daughter has now started to play the viola, so you will get a little bit of background noise here. I hope you can still hear this. If not, I'll cut this part out. The second term, though, is r times alpha in the theta hat direction. Well, what does that mean? This is actually the tangential acceleration. It's how much the velocity is increasing along the direction that it's moving. So this is saying that the size of this velocity vector is getting larger in the theta hat direction. Okay? So this is saying velocity is getting bigger. Whereas this is saying the velocity is changing direction. And at that point, we will stop, and you won't get the chance to hear the rest of my daughter's scales.